Welcome to Wisdom Docs. Settle in. Let your shoulders drop a little from wherever they've been carrying the day. There is nowhere you need to be for the next while. Nothing to solve, nothing to hold. Tonight, we are going to walk slowly into something very large and very old, and the largeness of it is the comfort, not the worry. So loosen your grip on the day. Let the pillow take the weight of your head. We have all the time in the world because the thing we are about to consider has already happened long ago, and it is finished, and it is quiet now. Here is the strange thing I want to lay in front of you, the thing that does not quite make sense the first time you hear it. 5,000 cubic kilometers of rock, roughly 50 Tamboras, 50 of the largest eruptions any human being has ever recorded, erupted out of the earth, and yet there is no mountain to show for it. Read that again, slowly, in the dark. The biggest eruption we know of in the whole history of the planet, and it left no peak, no cone, no volcano you could point to on a horizon and say, there, that is where it happened. The greatest explosion the Earth has ever managed, and it built nothing upward at all. That should bother you in a gentle, curious way. It bothered the people who first worked it out because everything we think we know about volcanoes tells us the opposite. A volcano is a mountain. That is almost the definition of the word in our minds. We picture the cone, the snow on its shoulders, the thin thread of smoke at the top, the slopes built up layer by layer over thousands of years by everything the Earth has thrown out of itself. Eruption means building. Eruption means a thing rises. So how can the single largest eruption ever found leave behind no rise at all? Where did the mountain go, and how could something so unimaginably enormous be today almost invisible, so quiet on the surface of the world that for most of human history nobody even knew it had happened? Hold those questions. We are going to answer them, all of them, slowly and properly, and by the time we are finished you will understand exactly why the largest eruption in Earth's history left no mountain behind. You will understand it well enough that it will feel obvious, the way true things do once you finally see them from the right angle, but we are not going to rush there. We are going to take the long, easy road because that is the only road worth taking when you are trying to fall asleep, and because the truth of this is more beautiful when you arrive at it gently. Before we go further into the dark together, I'd like to know where in the world you are listening from tonight, whether it's a city or a quiet road far from anywhere, whether it's late evening or the small hours of the morning where you are. If you feel like it, leave a word in the comments. I read them. And there is something companionable about knowing all these different rooms, all these different beds, all turn toward the same old story at the same hour. And if you are new here, if you've only just found this dock in the dark, you're welcome to stay. Settle in for more slow journeys like this one, whenever you need them, that's all. No more interruptions. From here on, it's just the story, and your breathing, and the slow descent. So, let us begin where every good mystery begins, with a place. The place is called La Garita, the La Garita Caldera. It sits in the San Juan volcanic field in the San Juan Mountains of southwestern Colorado, in the high, dry, broken country of the American West, where the land folds up into ranges of old, worn rock, and the air thins out and the silence at altitude has a particular weight to it. If you went there now, today, and stood somewhere in the middle of it, you would not know. That is the first surprising thing to hold on to. You could stand directly on top of the largest eruption in the history of the world and see nothing but ordinary mountains, ordinary slopes, ordinary forest and stone and sky. There is no warning sign written across the landscape. The mountains around you would look like mountains anywhere, eroded, ancient, patient. You would have absolutely no sense that the ground beneath your boots was the scar tissue of the most violent single thing the Earth has ever done. And the reason you would have no sense of it is the reason we are here tonight, because the eruption did not happen recently. It did not happen in any time a person could remember, or that any person's grandparents could remember, or that any human at all could remember, because there were no humans. It happened roughly 28 million years ago. Say that number to yourself slowly and let it stretch out. 28 million years, not 28,000. Not 280,000, 28 million. This was the Oligocene epoch, a chapter of the Earth's life so far back that it predates almost everything you might use as a familiar landmark in the deep past. There were no humans, of course, not even close. Our entire genus, the whole branch of the family tree that leads to you lying there in the dark, would not appear for tens of millions of years yet. When La Garita erupted, the world was being run entirely by other things. The eruption is so old that the mountains standing around its remains today are not the originals. They are remnants, reshaped, the worn-down children of a landscape that the eruption itself helped to make, and then time spent 28 million years patiently taking apart. So that is one part of the invisibility, the simplest part. 28 million years is enough time to hide almost anything. 28 million years of rain, of frost cracking stone in the cold and thaw releasing it in the warmth, of rivers cutting down through rock grain by grain, of wind carrying away the loosened dust a little at a time, of the slow, ceaseless work of erosion that never sleeps and never hurries and never stops. Given that much time, the Earth files almost everything down toward flatness. Given that much time, even the wound left by the largest eruption in history gets buried, dissected, softened, hidden. So when we say there is no mountain, we mean two things at once, and we will get to the second, deeper meaning later. But the first meaning is simply this: even if there had been something to see at the surface, 28 million years would have had a very long time to take it away. Now, before we go any closer to what actually happened, I want to make sure you feel the size of this thing, not the number. Numbers slide off a tired mind like water, but the actual scale, the real weight of it. Because the whole mystery only matters if you genuinely understand how enormous this eruption was. So let us build it up slowly, one step at a time, like climbing a staircase in the dark where you cannot see the top. Start with something you may remember or have at least heard of. Mount St. Helens. In 1980 in Washington State, not so very far north of where we are standing in Colorado, a mountain blew its side out in an eruption that made headlines around the world. It flattened forests, it killed people, it threw ash across the sky and turned day to a strange grey twilight for those nearby. It was, by the standards of a single human lifetime, an enormous and frightening event, the kind of thing that gets remembered for a generation. Mount St. Helens in that eruption threw out roughly 1 cubic kilometre of material. 1 cubic kilometre. Picture, if you can, a cube of rock and ash, a single kilometre on each side, a kilometre long, a kilometre wide, a kilometre tall. That is already more than the mind can really hold. That much rock, hurled out of the earth, was enough to make 1980 a year people in that region would never forget. Set that down on the bottom step of our staircase. 1. That is our unit. Hold it. Now climb a step. 11 years later, in 1991, on the other side of the world, a mountain called Pinatubo erupted in the Philippines. This one was bigger than St. Helens by a good margin. Pinatubo threw out something on the order of 10 cubic kilometers of material. 10 times our unit, 10 of those 1 kilometer cubes. And this was not a quiet event either. Pinatubo's eruption put so much fine material so high into the atmosphere that it actually cooled the entire planet measurably for a year or two afterward. The whole Earth ran very slightly cooler because one mountain in the Philippines had cleared its throat. 10 cubic kilometers, that is enough to nudge the global climate. Set it on the second step. 10. Already we are far beyond what feels comprehensible, and we have barely begun to climb. Take another step, and this one is a long one because now we leave living memory behind and reach back into recorded history to the largest eruption that any human being has ever documented. The year is 1815. The place is Tambora, on an island in what is now Indonesia. When Tambora erupted, it produced on the order of 100 to 150 cubic kilometers of total material, and even measured in the stricter way geologists prefer, counting only the dense rock equivalent of the magma itself, the most concentrated way of tallying it, it amounted to somewhere around 30 to 50 cubic kilometers. Either way, it dwarfs Pinatubo, dwarfs St. Helens entirely. And the consequences of Tambora were not subtle. The ash and gas it threw into the high atmosphere spread around the whole globe and dimmed the sun so much that the following year, 1816, became known around the world as the year without a summer. Crops failed in places thousands of miles from the volcano. Snow fell in months it had no business falling in. People who had never heard the name Tambora, and never would, on continents the eruption's ash had crossed, went hungry because of it. That is what 100-odd cubic kilometers can do. That is the largest eruption in all of recorded human history, the worst we have ever lived through and written down. Set Tambora on the third step, around 100, and take a breath here, because the next step is not really a step at all. Because now we come to La Garita, the Fish Canyon Tuff, and I will explain that name properly in a moment, but for now just hold it as the name of what La Garita produced. The Fish Canyon Tuff represents an erupted volume of approximately 5,000 cubic kilometers of magma, measured in that stricter, more honest way. The dense rock equivalent, the concentrated tally that strips away the fluff and counts only the solid substance of the thing. 5,000 cubic kilometers. Published estimates cluster somewhere around 4,500 to 5,000, but let us hold the round number because it is staggering enough. 5,000 cubic kilometers of rock erupted out of one place in southwestern Colorado 28 million years ago. Now go back down the staircase in your mind and feel the gap. Mount St. Helens was 1. La Garita was 5,000. That is roughly 5,000 times Mount St. Helens, not 5 times, not 50 times, 5,000 times the eruption that flattened forests and made global headlines and that people still talk about decades later. And compared to Tambora, the largest eruption humanity has ever recorded, the year without a summer eruption, the one that starved people on the far side of the planet, La Garita, was on the order of 50 times larger, 50 Tamboras. That is the phrase to fall asleep on. 50 of the worst eruptions in all of human history, all of their fury combined, and even that is only a rough way of pointing at the size of this single ancient event. And here is where the mystery begins to bite gently in the dark. 50 Tamboras, 5,000 St. Helens, and no mountain, no peak, no cone you can drive to and photograph. The most violent eruption the Earth has ever produced, and the surface of the world has almost nothing to show for it. How? Hold that. We are getting closer to the answer, but first we need one more piece of language, one more tool to think with, so that when we finally open up the mechanism, it will land with full weight. Volcanologists, the people who spend their lives studying these things, needed a way to compare eruptions to one another. a way to rank them, to put St. Helens and Pinatubo and Tambora and La Garita on the same shelf and say, this one was this much bigger than that one. So they built a scale. It is called the Volcanic Explosivity Index, and you will often see it shortened simply to VEI. And the most important thing to understand about this scale, the thing that makes it useful and also the thing that makes it slightly treacherous to the unprepared mind, is that it is logarithmic. That is a heavy word, so let me set it down softly. Logarithmic means that each step up the scale is not a little bigger than the step below. Each step up is roughly 10 times bigger. 10 times. Think of it the way you might think of the scale we use for earthquakes, if you have heard that one, where a step up is not a small increase but a leap into a different order of size altogether. The Volcanic Explosivity Index works the same way. A volcano rated, say, a 5 did not produce a little more than a 4. It produced roughly 10 times more. And a 6 is roughly 10 times a 5. And a 7 is roughly 10 times a 6. So each single step you climb on this scale is not a stair at all, but a whole flight of stairs. The numbers stay small and tidy on the page, 3, 4, 5, 6. But the reality behind them is exploding upward by a factor of 10 at every step. This is exactly the kind of scale that hides enormity inside small, calm-looking numbers, and that is worth remembering as we go. At the very top of this scale sits the number 8, VEI 8. There is no 9. 8 is the ceiling, the maximum category, the top shelf, and it is reserved for a particular class of event so large that volcanologists gave it its own name. They call these super eruptions. To qualify as a VEI 8 super eruption, an eruption has to eject more than 1,000 cubic kilometers of material. More than 1,000, remember our staircase. St. Helens was 1. Pinatubo was 10. Tambora was around 100. The threshold just to enter the highest category, just to be allowed in the door, marked super eruption, is more than 1,000 cubic kilometers, already 10 times the worst eruption in human history. Tambora, the year without a summer, the global catastrophe, Tambora does not qualify as a super eruption. It is not even close. It falls short of the threshold by a wide margin. The very largest thing we have ever witnessed and recorded does not make it onto the top shelf at all. And La Garita produced around 5,000 cubic kilometers, 5 times the threshold for the highest category on the entire scale. La Garita is not just a VEI 8, it is a VEI 8 sitting comfortably, enormously, far above the line that other super eruptions barely cross. It is one of the largest known explosive eruptions ever found anywhere in the geological record, frequently described as the largest single eruptive unit ever discovered. So far off the chart that the chart itself struggles to hold it, and yet still no mountain. Still that quiet country in southwestern Colorado, looking like ordinary mountains, hiding the largest wound the earth has ever opened in itself. Let me give the deposit its proper name now, the name I asked you to hold earlier, because we are going to be living with it for the rest of this story. The vast body of erupted rock that La Garita produced is called the Fish Canyon Tuff. A tuff. And this is a small piece of vocabulary you can let settle in without effort. A tuff is simply a rock made of volcanic ash and fragments that have come to rest and consolidated into stone. So the Fish Canyon Tuff is, in the plainest terms, the rock made from everything La Garita threw out and laid down. The eruption is the event. The Fish Canyon Tuff is what the event left behind, hardened into the ground. And it is this deposit, this Fish Canyon Tuff, whose volume we have been talking about all along, that 5,000 cubic kilometers measured as dense rock equivalent. I keep using that phrase, dense rock equivalent, and I want to make sure it is resting easily in your understanding before we go on, because it is the honest way to count an eruption, and it matters for everything that follows. When a volcano erupts, much of what it throws out is frothy and full of holes. Ash and pumice puffed up with gas, light and airy, taking up far more space than the actual solid material inside it would if you squeezed all the bubbles out. Pumice, you may know, is so full of trapped air that it floats on water, so if you simply measured the loose, fluffy pile of erupted material as it lies on the ground, you would get a misleadingly large number inflated by all that emptiness, all those bubbles. Dense rock equivalent is the careful correction for this. It asks, if you took all that frothy, airy, erupted material and squeezed every bubble out of it, compressed it back down into solid, dense rock with no gaps, how much would you actually have? It is the deflated, honest, no exaggeration figure, the true substance, stripped of all the air. And that is the figure we have been using when we say 5,000 cubic kilometres of magma erupted from La Garita, measured as dense rock equivalent. We are not counting the airy fluff. We are counting the squeezed down, solid, honest core of it. 5,000 cubic kilometres of genuine rock, which means the loose, frothy, fallen deposit before you squeeze it, spread across the landscape in volumes larger still. We are being conservative, careful, honest, and the number is still almost beyond holding. 50 Tamboras, 5,000 St. Helens, the top of the scale 5 times over. And here we are, ready at last to walk down into the great paradox itself, ready to ask the real question, Wolbia. If all of that erupted out of the earth, where on earth did the mountain go? But not yet. Not tonight, not in this first slow hour of our descent. We have laid the foundation, we have named the place La Garita Caldera in the San Juan volcanic field in the San Juan Mountains of southwestern Colorado. We have placed it in time, 28 million years ago, in the Oligocene, before any human breathed. We have built the staircase of scale, St. Helens at 1, Pinatubo at 10, Tambora at 100, La Garita at 5,000. We have learned the scale that measures these things, the volcanic explosivity index, logarithmic, each step 10 times the last, topping out at VEI 8, the super eruption, the threshold of 1,000 cubic kilometers that La Garita clears 5 times over. And we have named what it left behind the Fish Canyon Tuff, that vast deposit, measured honestly in dense rock equivalent. Let all of that sink down through you now, the way the ash itself once sank slowly out of the sky and came to rest on the ancient ground. You do not need to remember any of the numbers. They will keep. The mystery will keep. The mountain that is not there will still be not there in the morning. And the next time we descend together, we will go down into the mechanism of it, down into the moment the chamber emptied and the roof of the world lost its support and the ground itself decided, instead of rising, to fall. We will find out exactly where the mountain went. We will find that it went the only direction a thing that enormous could go, the direction nobody expects, and that the answer is so simple and so strange that once you see it, you will never look at a volcano the same way again. For now, though, just rest in the size of it. Rest in the comfort of something so immense and so finished, so utterly far away in time that it asks nothing of you, threatens nothing, demands nothing. 28 million years ago, in a place that is now quiet mountains and thin cold air, the earth did the largest thing it has ever done. And then it grew still. And the rain came and the rivers ran and the wind blew, and slowly, patiently, across an unimaginable span of years, the world settled over the wound and smoothed it and hid it and went quiet. The fury is long spent. The ash long since turned to stone. The story is already over, and we are only walking through its ruins by lamplight, in no hurry at all. So let your breathing slow to match the slowness of all that deep time. There is nothing here that can reach you. the largest eruption in the history of the world is 28 million years gone, and the mountains stand quiet over it. And you are safe in the dark, drifting down towards sleep, and we have only just begun to descend. Let me begin properly before the descent goes any deeper. Welcome to Wisdom Docs. If you are new here, and you find that this slow kind of voice helps you let go of the day, you might press subscribe quietly, the way you would close a door, so as not to wake anyone. And while you settle, I would like to know one small thing. Where in the world are you listening from tonight? A city, a quiet road, a room with the curtains drawn. Leave it below if you feel like it. No need to stay awake for it. Just a word, whenever. The comments are there in the morning. Now, let us name the place we are standing over. It is called La Garita Caldera. Say it slowly, La Garita. It lies in the San Juan volcanic field, in the San Juan Mountains of southwestern Colorado, a high and folded country of thin air and old stone, and the rock it left behind, the great sheet that is the only monument it ever raised, has a name too. The Fish Canyon Tuff. Hold those two names. They are the whole of where we are going. La Garita, the wound, Fish Canyon, the scar tissue, spread across the land, and the time we are standing in, the time we have to fall backward into to find them, is the Oligocene, roughly 28 million years ago, when there were no Rockies as you would know them, no people, no anything that would recognize a sky. And here, before we go a single step further down, is the thing that should not be possible. The thing the title promised you, and the thing your sleeping mind will turn over and over without ever quite catching. 5,000 cubic kilometers of rock erupted from this place. 5,000. And there is no mountain, none. You could walk the ground above it and never know. To feel the weight of that number, we have to climb a ladder. And we will climb it slowly, one rung at a time, so there is no rush in it. Begin small with something you might remember. In 1980, Mount St. Helens in Washington state took the top off itself in an eruption that people watched, that was filmed, that filled the news. It threw out roughly 1 cubic kilometer of material. 1. That single eruption felled forests for miles, darkened the sky, killed and reshaped a whole region. Hold that. 1 cubic kilometer. That is already more than the mind can really hold. Picture a cube of solid rock, 1 kilometer on every side. You cannot, really. Nobody can. But try gently and then let it go. Now step up the ladder. In 1991, in the Philippines, Mount Pinatubo erupted. That one was bigger, roughly 10 cubic kilometers, 10 times the size of St. Helens. Pinatubo threw so much into the high air that it cooled the entire planet measurably for a year or more. The whole world ran a fraction of a degree colder because one mountain breathed out. 10 cubic kilometers, 10 St. Helens stacked together. We are still in the world of things people have actually seen. Climb again. In 1815, on the island of Sumbawa in what is now Indonesia, a mountain called Tambora erupted. This is the largest eruption in all of recorded human history, the largest one any person has ever lived through and written down. Tambora produced on the order of 100 to 150 cubic kilometers of total material, something like 30 to 50 cubic kilometers of magma when you measure it as dense rock. The number we will use as we climb is that denser measure, the dense rock equivalent, the DRE, because it is the honest way to compare one eruption to another. The rock itself, with the froth and the air pressed out of it. Tambora was so large that the following year, 1816, was called the year without a summer. Crops failed across the northern world. There was frost in June. People starved because one mountain on the far side of the planet had filled the sky. That is the largest thing humans have ever witnessed, 100-something cubic kilometers, roughly 100 St. Helens, roughly 10 Pinatubos, the very ceiling of human experience. Now hold all of that, the whole ladder, St. Helens at 1, Pinatubo at 10, Tambora at the top of everything we have ever seen, and look up. Because La Garita is so far above the top rung that the ladder simply runs out. La Garita produced roughly 5,000 cubic kilometers of magma, measured as dense rock. 5,000. That is on the order of 5,000 times Mount St. Helens. It is roughly 50 times Tambora. 50 Tamboras, the largest eruption in human memory, 50 of them, all at once, from one place. The year without a summer came from a 50th of this. Stack 50 of the worst eruptions humanity has ever endured, pour them into a single event, and you are only just arriving at La Garita. And there is no mountain. There is a reason the ladder runs out, and it has a name too. Geologists measure the size of eruptions on something called the Volcanic Explosivity Index, the VEI, and the thing to understand about that scale, the thing that makes the size of La Garita finally land, is that it is logarithmic. Each step up the index is not one more, it is roughly 10 times more, the way each rung of our ladder was 10 times the one below. So the gaps between the numbers are not gaps at all, they are cliffs. A V5 is 10 times a V4, a V6 is 10 times that, and La Garita sits at the very top, at V8, the highest category the scale allows, the ceiling, reserved for the rarest events, the ones that throw out more than 1,000 cubic kilometers of material. There is a single word for an eruption that large: super eruption. La Garita is a super eruption, and even among super eruptions, at 5,000 cubic kilometers, it stands near the very top, far above the line where the category begins. And the strangest part, the part we will spend our long, slow descent unfolding, is that all of this immensity is written not into a peak, but into a sheet. The deposit, the Fish Canyon Tuff, is not a mountain you climb. It is a layer the land lies under. A vast horizontal blanket of welded ash spread out flat across the country and turned to stone where it landed. That is what 5,000 cubic kilometers of erupted rock looks like when it finally comes to rest. Not up, out. A floor, not a summit. The largest eruption we have ever found laid itself down sideways and went quiet, and the years buried it, and you would walk right over it. We will go down into how that happened, how a thing can be the biggest of all and still be all but invisible, how the absence of the mountain is not in spite of the size, but because of it. But not yet, for now the ladder has shown you its last rung, and there is nothing above it, only the open sky, only the number 5,000 hanging there in the dark above the high, cold mountains, where it all came to rest a very long time before anyone was here to be afraid of it. Let that number settle over you the way the ash once settled over the land, slowly, evenly, until everything beneath it grows still. The question that the title puts in your hands, the one that has been patient enough to wait through the scale and the numbers and the long, quiet ladder of comparisons, is this: where did the mountain go? Not where is it now, not what became of it over millions of years of weather and erosion, but something more fundamental than that. Why was there never a mountain to begin with? Why does the largest eruption we have ever found leave behind a flat stone sheet rather than a peak, a wound rather than a summit, a hole in the earth rather than something rising above it? The answer lives in the mechanism. And the mechanism, once you have seen it clearly, changes the way you understand what a volcano actually is. Begin with what most of us carry as a picture when we hear the word: a mountain, a cone, a thing that builds itself upward over time as material piles on material, layer by layer, century by century, until it stands high enough to catch snow, and pull clouds around its shoulders. This is the stratovolcano, the kind most of us have in mind when we think of the word volcano at all. Mount St. Helens before 1980, Mount Fuji, Vesuvius above the bay at Naples. These are constructed things, patient accumulations. The eruptions that build them are explosive, yes, but they are partial. They throw out a portion of what is below and then pause, and the mountain remains, and the next eruption adds another layer, and over time the cone grows. The mountain is the record of many eruptions, each one incomplete, each one leaving the structure standing. What happens at La Garita is not this. What happens at La Garita is closer to what happens when you remove the support from beneath a vast and heavy ceiling. When enough material drains away from below, the structure above it does not continue to stand, it falls. But to understand the falling, you have to understand what was there before the eruption began. Beneath the land that would become the San Juan Mountains of southwestern Colorado, roughly 28 million years ago in the Oligocene epoch, there was a magma chamber of extraordinary size. This is not unusual in principle. Magma chambers exist beneath active volcanic regions across the planet. They are not neat, empty caverns of glowing liquid, though that image is a reasonable place to begin. Think of them instead as zones within the rock itself where the proportion of molten material is high enough that the whole mass behaves more like a fluid than a solid. The surrounding rock is partly melted, partly crystallized, permeated with hot, silica-rich melt under enormous pressure from the weight of everything above it and from the heat driving upward from below. The chamber, beneath what would become La Garita, was feeding on heat and material delivered from far deeper in the earth, from processes that we will come to in the next movement of this story. For now, what matters is the pressure. The chamber had been accumulating, building pressure the way a vessel builds pressure when you add heat to a closed container and cannot release it. Millions of years, possibly, of slow accumulation. The rock above it, kilometers of it acting as a lid, holding everything down, holding everything in, until it could not. When the lid fails, it does not fail gently. The pressurized magma, finding a pathway, finding the fractures and weaknesses in the crust above it, erupts with a violence proportional to how much pressure has been stored and how much material is available to release it. At La Garita, the answer to both of those questions was an almost incomprehensible amount. And here is where the mechanism diverges completely from the picture of the building cone. In a stratovolcano, the chamber below is comparatively small, and the eruption draws from a reservoir that is not emptied all at once. The plumbing remains intact. The structure above it remains supported. But at La Garita, what was happening was the catastrophic, rapid emptying of an enormous magma system. Not a partial draw from a deep reserve, but a wholesale evacuation. 5,000 cubic kilometers of material, dense rock equivalent, moving upward and outward in a geologically eye blink of time. A quantity so vast that the space it occupied could not simply be left as a hole in the middle of the crust without consequence. Think of it as an engineering problem. The roof of the chamber, which is to say the kilometers of solid rock sitting above the magma, is held up by the pressure of what is below it. The magma is not just filling space, it is, in a mechanical sense, supporting the ceiling. When you drain the chamber rapidly and catastrophically, you remove that support. And when you remove the support from a ceiling of solid rock kilometers thick and tens of kilometers wide, the ceiling does not arch gracefully downward. It collapses. This is caldera collapse. This is how the mountain went down instead of up. The roof rock, losing its foundation, fractures along great ring-shaped faults that trace the margins of the emptying chamber below. These faults are not cracks in the ordinary sense. They are vast architectural failures, kilometers deep, running in rough circles or ovals around the collapsing center. Along these faults, the ceiling drops, not all at once, not in a single clean descent, but in a catastrophic foundering, block by block, section by section, the massive carapace of rock above the evacuating chamber sinking downward into the space the magma once occupied. The material that was there goes out and away. The material that was on top comes down into where it used to be. What is left behind is a caldera, not a crater, which is the small bowl at a volcano's vent, but a caldera from the Spanish word for cauldron, a vast sunken basin bounded by those ring faults, the topographic signature of a chamber that once was full and then was emptied so fast that the world above it fell in. The Garita Caldera, the scar left by this collapse, is one of the largest such structures known on Earth. Its dimensions are commonly given as approximately 35 by 75 kilometers, that is to say, about 22 miles by 47 miles, an oval basin large enough that if you placed a moderately sized city at its center, you would not be able to see the rim from the city's streets. Some assessments of the original structure before the millions of years of erosion and deposition and later volcanic activity that have altered it suggest it may have extended up to roughly 100 kilometers in its longest dimension, a scale that begins to strain the imagination's ability to hold it as a single thing. Stand at one end of that basin and the far rim is below the horizon. The structure is not a landscape feature in the ordinary sense. It is a landscape. You are inside it, and you do not necessarily know it. The San Juan Mountains rise and fall around you, beautiful in their way, eroded and carved by 35 million subsequent winters and the patient work of rivers, and somewhere beneath you and all around you are the ring faults, the margins of the collapse, the evidence of what this place was. The greatest eruption we have ever found did not leave a mountain. It left a hole. A caldera 35 by 75 kilometers wide, at the minimum, a wound in the crust of the continent, and the evidence of the eruption itself spread out not vertically but horizontally in every direction from the source in a layer that covers thousands of square kilometers of the land around it. That layer has a name: the Fish Canyon Tuff. And to understand what it is and why it looks the way it does and why it is the proper monument to this kind of eruption, you need to understand what came out of the ground before the ceiling fell in. When the pressurized system below finally breached, what emerged was not a single column of rock and gas shooting skyward in the way the mind's eye might prefer. At some scales of eruption, that column model holds. A plume rises high into the stratosphere, and then the material falls back out of it over days and weeks, dusting everything downwind in fine ash. This is the signature, for example, of the Pinatubo eruption in 1991, and it is spectacular, but it is, by the measure of La Garita, small. At volumes many orders of magnitude larger, the dynamics change fundamentally. What flows from the vents at a super-eruption scale is something different. It is a pyroclastic density current, and it moves not upward but outward. Picture, if you can, a mass of incandescent gas, ash, pumice fragments and rock, all mixed together at temperatures that can reach several hundred degrees or more, and all of this moving not as a rising column, but as a ground-hugging avalanche, flowing outward from the source, the way a liquid spills from an overturned vessel, following the contours of the land, pouring into valleys, crossing ridges, spreading in all directions from the collapsing caldera. These currents move fast. The speeds involved in pyroclastic density currents range from tens of kilometers per hour to well over 100 kilometers per hour. You could not outrun one. There would be no warning in the conventional sense that the word warning usually carries. By the time you perceived it, it would already be upon you. The temperature alone would be lethal at distances from the source that dwarf anything we associate with ordinary volcanic hazard. And behind the heat comes the kinetic force of an avalanche that can level forests and reshape the ground it passes over. At La Garita, 28 million years ago, in a landscape that held no human observers and no cities and no forests in the form we would recognize, these currents spread outward from the collapsing system across what is now the San Juan volcanic field. They moved across the high terrain of what would become southwestern Colorado, filling valleys, burying whatever lay beneath them, spreading in great sheets that covered the land the way a river delta spreads when it reaches flat ground, except that this was not water but incandescent rock, glowing and moving and so enormously thick in places that the material at its base could not lose its heat to the air. This is the crucial point. This is why the Fish Canyon Tuff is what it is, and not simply a layer of loose ash. When a pyroclastic density current is thick enough, and when it carries enough heat, and when it comes to rest on the landscape, the material at its interior does not cool quickly. The lower layers are insulated by everything above them. The particles, the fragments of pumice and ash and glass, are still hot, still plastic in a physical sense, still capable of being deformed. And under the weight of hundreds of meters of material pressing down from above, and in the presence of that retained heat, the particles begin to fuse. This process is welding. The glass shards and pumice fragments in the interior of the deposit, still soft enough to deform, are pressed together under their own weight, and they stick and they seal, and what was loose granular material becomes, over the time it takes to cool, a solid rock. Not cemented by a later process, not hardened by groundwater depositing minerals between the grains, but welded from within, the particles having physically merged under heat and pressure, while the whole mass was still at elevated temperature. The result is welded tuff, and the Fish Canyon Tuff is one of the most extensive and best characterized examples of this rock type anywhere in the geological record. Drive through the San Juan Mountains today, and you encounter it in road cuts and canyon walls, a dense, pale, often pinkish or grey rock that sits in massive, nearly structureless sheets, betraying in its very texture the way it formed. Not from particles that settled slowly through water, not from grains cemented over long periods, but from a mass that arrived hot and thick and fused itself into stone. Where the deposit was thinner, at its outermost margins where the current had lost most of its heat and depth before coming to rest, the tuff is not welded. The particles cooled too fast with too little overlying weight to compress them. At those edges, the material remains as loose or partially consolidated ash and pumice, the less durable margins of the deposit that erosion has worked on, preferentially for 28 million years. But at the center, near the source where the deposit was hundreds of meters deep, the welding is intense. The Fish Canyon, tough in those zones, is hard, resistant rock, and it has lasted. It is exposed today across thousands of square kilometers of the San Juan Mountains region, recognizable to geologists who have learned its character, its chemistry, its age, and it lies in sheets, in flat or gently inclined layers, following the topography of the landscape that received it, rather than standing above that landscape as a peak. This is the monument. This is what 5,000 cubic kilometers looks like when it has settled. The monument is a floor. The monument is the ground you walk on in places, the walls of canyons cut by rivers that came long after, the flat benches on hillsides that the eye takes for natural terraces, but that are in fact the upper surface of a welded sheet that formed in a single, catastrophic event. Not a mountain, a buried, durable, horizontal record. This is why the absence of the mountain is not in spite of the eruption's size, but because of it. The very magnitude of the event, the sheer volume of material released in so short a time, guaranteed a different outcome than the slow construction of a cone. An eruption of this scale does not build, it drains and collapses and spreads. The stratovolcano and the caldera supereruption are not different points on the same spectrum. They are different phenomena governed by different geometries, different scales of magma supply, different mechanical outcomes. One accumulates, the other evacuates. And the evacuation at La Garita's scale produced a lateral sheet of stone and a sunken basin where the roof fell in, and nothing above the surrounding land, nothing that rises against the sky the way a mountain rises. The crust itself in the aftermath of the collapse was not static. The evacuation of so much material from below and the collapse of so much rock from above into the emptied space did not represent a final equilibrium. The magmatic system below, though greatly diminished, was not dead. Pressure continued from whatever remained of the melt, from the slow movement of heat from depth. And this continuing pressure had a new effect, a subtler one, but one that geologists who study these systems have learned to recognize, and that adds a final layer of strangeness to the story. After a large caldera collapse, the floor of the new basin can, in some systems, be pushed back upward, not to the level it started at. Not enough to rebuild what was lost, but enough to form a dome, a broad and gentle swelling in the center of the collapsed depression where the floor, under continuing pressure from the magmatic system below, begins to rise again. This structure has a name. It is called a resurgent dome or a resurgent uplift, and it is one of the signatures that distinguish a true large caldera system from smaller volcanic features. The San Juan volcanic field, including features associated with the La Garita system, shows evidence of resurgent structures. The caldera, having collapsed, began in some measure to reassert itself, to push back against the depression it had created, the floor bowing gently upward as the pressure below refused to entirely relent. This is not a dramatic reassertion. It is not a second eruption in the same category. It is a slow geological readjustment, the kind of thing measured in hundreds of thousands or millions of years rather than in human lifetimes. But it means that a large caldera is not simply an inert wound after the collapse. It is a system that continues, that breathes in its slow geological way, that has a second act even after the catastrophic first one. The La Garita structure, by the time the Oligocene gave way to later epochs, was already something the Earth was slowly digesting and reworking. Subsequent eruptions in the region, other calderas forming in the multi-million-year pulse that we are going to follow in the next part of this descent, overlapped and complicated the structure. Later, volcanic material covered parts of it. Rivers cut into it. The ice ages shaped it. Erosion, patient and indifferent, has been working on it for 28 million years. And this too is part of the answer to the question of why it is nearly invisible. The eruption itself did not leave a towering peak. The caldera collapse left a basin, but the basin did not remain a neat, clean, empty bowl. 28 million years of geological history filled it, modified it, buried some of it, eroded other parts, and left it as something that does not announce itself to the untrained eye. You need to know how to read the landscape at a scale and with a vocabulary that takes years to acquire. The ring faults are there, traceable if you know what to look for, the curved structural lines that mark where the ceiling fractured and dropped. The Fish Canyon Tuff is there in the canyon walls and road cuts, the welded grey rock that formed in a day or a week or whatever span of time the current required to cool. The shape of the depression, the broad oval of the caldera itself, can be traced on topographic maps and geological surveys, visible once you know the pattern you are looking for. But from the air, from a casual distance, from the window of a car moving through the San Juan Mountains, it does not look like the site of the largest eruption in Earth's known history. It looks like mountains. Old, eroded, beautiful mountains with the light coming across them in the late afternoon, and the shadows filling the valleys and the creeks running cold and clear at the bottom of the canyons. There is nothing about the surface view that says, here. Here is where a thing happened that dwarfs every volcanic event in recorded human time. Here is the caldera of La Garita, the source of the Fish Canyon Tuff, the largest single eruptive unit we have ever found. The evidence is there. But it is patient. It has been patient for 28 million years, and it will be patient for 28 million more. It does not need to announce itself. The rock knows what it is. And this quality of hiddenness, of the enormous hidden inside the ordinary-looking, is perhaps the most appropriate monument of all to an event that the Earth has thoroughly finished with. The wound closed. Not quickly by any human standard, but the geological clock measures differently, and 28 million years is more than enough time for a landscape to grow back over even the largest scar, for rivers to establish their courses, for the caldera floor to be buried and modified and partially healed from below, for everything on the surface to settle into a new arrangement that gives no immediate sign of what lies beneath it. Somewhere in the canyon walls of the San Juan Mountains, in the rock that catches the afternoon light and glows in the colors of old stone, the Fish Canyon Tuff sits in its massive horizontal sheets, the direct physical record of those pyroclastic density currents that moved across this landscape in the Oligocene, the hot avalanches of gas and ash and pumice that cooled and welded and turned to stone and have been lying there ever since, not going anywhere, not diminishing, just there in the way that very old and very durable things simply are there, requiring nothing, indifferent to whether we find them or understand them or even know to look. The roof fell in, the currents spread out, the ash welded into stone. The basin, in its slow way, began to readjust, and the landscape grew back over it the way landscapes always do, indifferent to what lies beneath, concerned only with the work of the present, the rain and the frost and the river and the wind. This is the mechanism. This is how a thing can be the biggest of all and still be almost invisible. The mountain did not fail to form through any deficiency in the eruption. The mountain did not form because the eruption was too large, too fast, too complete, too total in its evacuation of the chamber below to permit the ordinary incremental construction of a cone. It built, instead, in the only direction available to it, outward, across the landscape, in a sheet, in a layer, in the rock that is still there if you know how to look and have the patience to read the ground beneath your feet. But this is only the surface of the story. The mechanism tells you what happened during and after the eruption, the collapse and the currents, and the welding and the basin and the slow resurgence. What the mechanism does not yet tell you is what was already strange and remarkable about the magma itself before it ever left the ground. What was waiting below the land, building its pressure before the day the lid finally failed. The magma that became the Fish Canyon Tuff was not a simple liquid. It was not the straightforward fluid that the word magma might suggest, the glowing, easily flowing melt that we see in images of Hawaiian lava rivers moving toward the sea. The Fish Canyon magma was something more complicated than that, more counterintuitive, more strange. And the strangeness of it, the particular character of what was building beneath the San Juan volcanic field in the Oligocene, is part of what makes the La Garita eruption not just the largest known, but one of the most scientifically interesting, an eruption that should not, by some intuitions, have been able to happen at all. The Fish Canyon magma was a crystal mush. That phrase carries more weight than it might first seem to, so let us stay with it for a moment before moving on. When geologists examine the preserved mineral content of the Fish Canyon Tuff, the welded sheet lying across the San Juan Mountains, the rock that is the eruption's only monument, they find that the magma from which it came was roughly 40 to 45% crystalline by volume, solid crystals suspended in melt making up nearly half the total body of material waiting below the ground. Imagine not a liquid, but something closer to a saturated slurry, a thick suspension of mineral grains moving sluggishly through the remaining melt under enormous pressure in the dark. This is the material that erupted in the greatest single outpouring the geological record preserves, a body of magma so laden with its own crystalline structure that it should, by simpler intuitions, have been nearly incapable of the explosive violence it achieved. And yet, The question of why such a body erupts at all, why a crystal-rich dacite, viscous and sluggish by nature, would suddenly and catastrophically exit the chamber rather than simply sitting, cooling, slowly crystallizing further toward the point where no eruption is any longer possible, is one that the La Garita event forces upon any honest treatment of the subject. The answer is not a simple one. But the beginning of it lies not in the magma chamber itself, not in the San Juan volcanic field, not even in the crust of southwestern Colorado. It lies much deeper in the slow and grinding behavior of a tectonic plate that no longer exists, the Farallon Plate, a vast section of oceanic crust that for tens of millions of years was moving eastward beneath the western margin of the North American continent, descending, subducting into the mantle at an angle, dragging itself down and under with the patient and enormous force that plate tectonics alone can generate. The Farallon Plate is gone now, consumed almost entirely, its remnants preserved only in small fragments that geologists call the Juan de Fuca and Cocos plates along the modern Pacific margin. But in the Oligocene, 30 million years ago and earlier, it was very much present, very much moving, and its behavior was changing in ways that would ultimately be felt at the surface in the most violent manner the solid Earth is capable of. What happened, as best the models allow us to reconstruct, is this. The angle of the subducting slab began to steepen. The Farallon Plate, as it continued to descend, rolled back, the leading edge pulling deeper and away from the continent, opening a gap between the underside of the North American crust and the descending slab. Into that gap, hot material from the asthenosphere, the partially molten layer of the upper mantle, was able to rise, and rising hot asthenosphere beneath a thick continental crust is, in the language of geology, an efficient recipe for catastrophic melting. The crust, rich in silica, rich in the minerals that produce viscous, gas-charged, explosive magma, began to melt from below in volumes that the San Juan Mountains themselves, raised and eroded and raised again over the intervening ages, can only partially reflect. This is what the ignimbrite flare-up was. Not an accident, not a random fluctuation in the Earth's interior. It was a consequence, a continental-scale response to the changing geometry of a descending plate, a pulse of crustal melting that lasted millions of years and generated dozens of eruptions, scores of calderas, vast sheets of welded tuff laid one upon another across the landscape of what is now the American Southwest. The San Juan volcanic field alone contains at least 15 to 20 identified calderas. La Garita was the loudest voice in a chorus that had been singing, at various pitches and intervals, for perhaps 10 million years before the Fish Canyon magma finally found its way out, and so the La Garita eruption was not a freak, it was a culmination. But culminations have mechanisms, and the mechanism, the specific chain of physical events that turned a crystal-rich dacitic mush sitting in a chamber somewhere beneath the Oligocene Colorado landscape into the largest single eruptive event the geological record knows, runs as follows. The chamber filled. Over time, over perhaps hundreds of thousands of years of slow accumulation and gradual pressure increase, the magma body grew. It grew in volume and in the pressure it exerted on the surrounding and overlying rock. Dissolved gases, water vapor, carbon dioxide, sulfur dioxide, remained locked in the melt under the confinement of that pressure, the way gas remains dissolved in a sealed bottle, waiting for the moment when the seal is broken and the pressure released. The roof of the chamber, the rock above, kilometres of it, sitting over the magma like a lid, held. And then at some threshold that the remaining evidence does not allow us to identify precisely, it did not hold any longer. What followed happened in the language of catastrophe, which is to say quickly, devastatingly, and with a completeness that left almost nothing of the ordinary structure intact. The roof failed. The magma, under enormous pressure, began to escape. Not in a single, neat upward column as a smaller eruption might produce, but in a distributed, violent, lateral, and upward outpouring that fed not a plume of ash rising into the stratosphere in a focused column, but a spreading, ground-covering avalanche of material moving outward from the eruption site in every direction at once. These are the pyroclastic density currents, ground-hugging avalanches of incandescent gas and ash and pumice moving at speeds that are difficult to hold in the mind alongside the word rock. Tens of kilometers per hour in larger or more energetic flows, over 100. The material is hot enough to glow. It is moving fast enough to outrun anything that moves on the surface of the earth. And it is dense enough, heavy enough to hug the ground rather than rising, to fill valleys, to pour over low ridges, to advance across the landscape in a continuous destroying wave, depositing its material as it goes, leaving it behind in layers that, where the flow was thick enough and hot enough and the material close enough together, began almost immediately to weld. Welding. This is the process that turns a pyroclastic deposit into the rock that the Fish Canyon Tuff now is. The rock you can stand on in the San Juan Mountains today and know that you are standing on the monument of the event, on the eruption's own hardened body. The ash and pumice particles, deposited in a layer that in some places reached hundreds of meters in thickness, were still hot when they came to rest. Hot enough that the particles retained their plasticity, and under the weight of everything above, hundreds of meters of material pressing down, the particles began to fuse. Not melt exactly, fuse. Glass fragments flattening and flowing into one another, pumice clasts collapsing and compressing, the whole mass gradually becoming coherent, becoming solid, becoming the welded tuff that is now the visible and measurable record of what happened here 28 million years ago. The result is a sheet, horizontal, vast, and in places of extraordinary thickness, not a cone, not a peak, not the mountain that intuition would have predicted from an eruption of this magnitude. A sheet spread across the landscape the way a catastrophic flood spreads, not upward, but outward, covering thousands of square kilometers, recording the event not as a summit, but as a floor, as a buried and exposed stratum that a geologist can read the way a reader reads a page, if the geologist has the training and the patience and knows what signs to look for in the rock. And above the sheet, nothing where the mountain might have been, or rather, something that is in its own way more remarkable than nothing, because as the eruption emptied the chamber below, and the chamber did empty catastrophically, completely, or near enough to completely, that the distinction is largely academic. The roof rock above it lost the support that the pressurized magma had provided. The rock that had been held up, in the way a ceiling is held up by the material beneath it, was now suspended over a void, and rock, given sufficient time, given sufficient scale, given no other option, does what gravity always insists upon. It falls. The caldera collapse at La Garita was not a gradual process. It was not the slow settling of a landscape over years. It was the foundering of an enormous block of crust into the space vacated by the erupted magma, a downward movement along ring faults that traced the margins of the chamber below, a sunken basin produced not by erosion, not by weathering, not by the ordinary patient work of surface processes, but by the instantaneous, in geological terms, failure of the chamber roof under its own weight and the withdrawal of its support. The mountain did not fail to form, the ground went the other way. The dimensions of what remained, the La Garita collapse structure as geologists map it today, working from exposure patterns and rock types, and the geometry of the faults that bounded the collapse, are approximately 35 kilometers by 75 kilometers, 22 miles by 47. Some estimates, accounting for the modifications of 28 million subsequent years, suggest the original depression may have extended to perhaps 100 kilometers in its longest dimension before erosion and burial and later geological events began to obscure the boundaries. It is one of the largest caldera structures identified on Earth. A wound in the crust of a scale that has no ready comparison in any landscape a living person has walked through and tried to comprehend as a single thing. And it is when you begin to ask, what exactly was inside that chamber before it emptied so catastrophically, that the story becomes strange in a different way, because the magma that produced the Fish Canyon Tuff was not the straightforward liquid most people carry in their minds when they think of erupting rock. It was not a molten river, not a fluid body moving freely through channels in the crust the way water moves through soil. It was something considerably more unusual. Something that the first-time geologists characterized it fully prompted a revision of how they thought about the relationship between magma and time. The Fish Canyon magma was a crystal mush. That term deserves a moment. A mush, in the geological sense, is exactly what it sounds like, a body of material that is neither fully solid nor fully liquid, but something occupying the uncomfortable middle ground between the two. Think of it the way you might think of very cold honey that has begun to crystallize, still moving if you press it, still capable of flowing given enough pressure, but thick with solids, laden with structure, not the clean fluid the word liquid suggests. Or think of a jar of peanut butter left in the refrigerator overnight. It will pour eventually under enough force, but it does not pour easily, and it does not pour fast, and it does not pour anything like water. The Fish Canyon magma was like that, except the crystals suspended within it were not sugar or fat molecules. They were minerals: sanidine feldspar, biotite, quartz, hornblende. Real crystalline structures that had grown slowly over vast stretches of time within the body of the magma as it sat in the chamber and cooled again and maintained a kind of suspended, barely liquid patience. And they made up, by volume, somewhere between 40 and 45% of the entire magma body, nearly half. In a body of magma that, we have already established, eventually erupted somewhere in the neighborhood of 5,000 cubic kilometers. That is a staggering thing. Picture it again, not in abstract volumes, but in the material reality of what it means. Nearly half of 5,000 cubic kilometers to perhaps 2,000 kilometers or more of actual, solid, grown mineral crystals, suspended within a liquid silicate, melt and waiting. Waiting for the pressure to release. Waiting for the roof above to thin. Waiting in the geological sense that has no impatience in it for the conditions that would allow the mush to move. And this is where the science becomes genuinely counterintuitive, because common sense suggests, and volcanology spent a long time partly agreeing, that a magma body this crystal-rich, this viscous, this laden with solid material should be less dangerous than a clean, hot, fluid melt. It should be sluggish, it should be difficult to erupt. A stiff slurry, you might reasonably imagine, does not explode. It oozes, it squeezes, it resists at great volume the kind of catastrophic, rapid decompression that produces the pyroclastic currents and the airborne ash columns and the welded tough sheets of a true super eruption. And yet, the Fish Canyon magma erupted 5,000 cubic kilometers. It erupted it explosively. It laid down the largest single eruptive deposit we have yet identified in the geological record, the crystal mush under the conditions that eventually developed at La Garita 28 million years ago, did not resist. It failed entirely and catastrophically, and at a scale that still has no living witness. The resolution to this apparent contradiction is still a matter of active research and careful debate among volcanologists, but the broad shape of the answer goes something like this. A crystal mush at depth is held together and held in place partly by its own viscosity, partly by the confining pressure of the rock above it, and partly by the chemistry and temperature of the melt that still flows between its crystal framework. Change any of those conditions sharply enough, reduce the pressure above, introduce new hot melt from below, allow the dissolved gases within the melt to begin exsolving, to begin coming out of solution the way carbonation releases from a shaken bottle. And the mush does not simply begin to flow, it can fragment. The melt between the crystals, saturated with dissolved water and carbon dioxide and sulfur compounds under the immense pressures of depth, suddenly finds those pressures gone, and it expands violently, transforming from dissolved gas to free gas, and the fragmentation is explosive in the most literal sense. The crystals and the melt and the gas become, together, the pyroclastic mixture that then travels outward and upward and eventually down the flanks of a collapsing landscape at speeds no living creature in the vicinity would survive. The high crystal content in this reading is not a safety factor. It is a record. It tells us how long the magma sat there, accumulating crystals slowly over perhaps tens of thousands of years, building toward a threshold it had not yet reached. And then, when the threshold arrived, erupting so quickly that those crystals, all those patient minerals, were carried out intact, preserved in the tuff that buried the landscape beneath. The crystals in the Fish Canyon Tuff are a diary of waiting, and the eruption was the moment the diary ended. There is something in that which asks for a slow breath. The image of it, a body of crystal-laden melt, sitting at depth beneath what is now the San Juan Mountains of southwestern Colorado, growing its minerals grain by grain, year by year, millennium by millennium, in the deep dark and the heat of the crust. Patient, not because it had any intention, but because geology does not hurry. And then, in some interval that would register on the geological timescale as almost nothing, the release. The catastrophic failure. The 5,000 cubic kilometers moving outward across a landscape that had no mountains yet. No Rockies as we would recognize them, nothing but the empty Oligocene terrain under a sky we could not breathe. But to understand why it happened at all, not just how the mush erupted once it began, but why the conditions for such an eruption arose in the first place, you have to go deeper. Deeper in space, beneath the crust entirely, into the slow machinery of the mantle and the moving plates, and you have to go to a plate that no longer exists, the Farallon Plate. The name belongs to an oceanic plate that spent tens of millions of years slowly disappearing beneath the western edge of North America, descending into the mantle in the process geologists call subduction. Subduction is the mechanism that consumes oceanic crust, pulling the dense seafloor rock downward beneath the lighter continental crust along the coast, feeding it into the mantle where the heat is sufficient to melt it and recycle it. The Farallon Plate was, in its time, vast. It underlaid much of the eastern Pacific and converged with North America along what is now the western coast, driving down at an angle beneath the continent and carrying with it, as subducting plates do, water and carbon dioxide and other volatile compounds locked in its minerals. That water matters. When it is released from the descending slab at depth, it lowers the melting point of the mantle rock above the slab, triggering partial melting and producing magma that rises buoyantly through the overlying rock. This is the standard subduction engine, the machinery responsible for the arc volcanoes that ring the Pacific, Mount St. Helens, Pinatubo, the whole chain of them, where a subducting plate provides the volatile flux that keeps a volcanic arc alive above it. But the Farallon plate did not behave consistently. Its behavior changed over tens of millions of years, and one of the changes that most concerns the story of La Garita is the change in the angle and configuration of the slab's descent, what geologists describe as slab rollback. This is a process in which the hinge point where the slab begins to descend retreats oceanward, causing the angle of the slab to steepen, and in doing so allowing the asthenosphere, the hot, partially molten layer of the upper mantle that lies beneath the rigid lithosphere, to flow in behind and beneath the continent from which the slab was pulling away. Think of it this way. Imagine a heavy blanket being slowly pulled off the edge of a bed, the leading edge of the blanket angling downward toward the floor. And imagine that as the blanket slides away, the warm air beneath the room flows inward to fill the space it vacated, that warmth pressing upward from below against the mattress it was no longer insulated from. The asthenosphere moving in beneath Western North America during the period of slab rollback was something like that warmth. Hot mantle material suddenly in contact with continental crust it had been separated from while the slab was flat and thick between them, now pressing upward and delivering immense thermal energy directly to the base of the lithosphere. The effect of that heat delivered to crust that was already silica-rich, already of a composition that melts at lower temperatures than the more primitive rocks of the mantle itself, was widespread, sustained, and profound. The crust began to melt, not in isolated pockets, not in thin veins, but in enormous volumes, producing the silicic magma, the dacitic, the rhyolitic, the crystal-laden melts that eventually fed what would become the ignimbrite flare-up, the San Juan volcanic field, La Garita, the Fish Canyon Tuff. The eruption in this frame was not an accident. It was not a quirk of local geology or a coincidence of pressure and timing. It was the surface expression of a change in the architecture of the entire western edge of a continent. The Fish Canyon Tuff is a message written in 5,000 cubic kilometers of fused ash and crystal, and the message, read slowly, says, "Here is where the deep machinery of the earth changed direction, and here is the mark it left on the surface when it did. That mark is still there. Changed, eroded, buried in places and exposed in others, but there." And the story of how the mark is read, of how the structure that remained after the eruption and the collapse is understood today, requires following the landscape through time, through the tens of millions of years between the Oligocene and the present, during which the wound at La Garita did not simply sit unchanged, but was acted upon by forces that partially healed it, further obscured it, and ultimately made it one of the more demanding puzzles in field geology to recognize at all. The first process is one that might surprise you because it works in the opposite direction from the collapse. After the catastrophic foundering of the caldera roof into the emptied chamber, after the sunken basin took on its initial dimensions, 35 by 75 kilometers of down-dropped crust, one of the largest single structural collapses the continents record, the story did not end. The magma chamber that had just evacuated billions of tons of its contents was not empty in any permanent sense. Magma at depth does not simply disappear. The supply from below, the slow upwelling of partially molten rock driven by the same asthenospheric heat that had produced the eruption in the first place, continued. And the continued supply of magma at depth pressing upward into the base of the collapsed block had nowhere obvious to go, but it could push. The caldera floor, the newly sunken roof rock that had dropped downward into the void, found itself acted upon from below by a pressure that had not fully resolved, and in some calderas, not all, but a recognizable pattern among the large ones, that continued upward pressure causes the central portion of the collapsed floor to bow upward again, rising like the center of a plate pressed from below. The margins, bounded by the ring faults that formed during collapse, remain down-dropped, but the interior rises, forming what volcanologists call a resurgent dome, a broad, gentle uplift within the sunken basin, the sign that the magmatic system is not finished, that pressure still exists at depth, that the wound is being partly, slowly, incompletely, pushed closed from inside. Several of the calderas in the San Juan volcanic field show evidence of resurgent structures, and features associated with La Garita are included among them. The resurgence does not restore the landscape to anything like its pre-eruption state. It does not rebuild a mountain. It raises the caldera floor somewhat, tilting and fracturing the tuff layers already deposited within the basin, creating a gently domed interior that geologists can read in the orientation of rocks and faults, but that would not register to an untrained eye as anything more than the subtle topographic contours of an old and heavily modified landscape. The healing is real, but it is partial, and it is slow, and it operates over the same timescale as everything else in this story. Millions of years during which other processes are simultaneously at work. The most patient and most thorough of those other processes is erosion. 28 million years is a very long time to leave a landscape to the rain and the wind, and the freeze-thaw cycles that split rock along hairline fractures, and the rivers that form and migrate and carve and carry, and the ice, during the several glaciations of the more recent past, that advanced across the San Juan Mountains and scraped and plucked and transported. All of that applied for 28 million years to a volcanic landscape already deeply fractured by the collapse and the resurgence, produces something that looks nothing like a caldera in any simple illustrative sense. The image most people carry of a caldera is Crater Lake. A clean, circular depression, walls rising sharply around a lake of remarkable blue, obviously a collapsed volcanic structure, even to a child looking at a photograph. Crater Lake is roughly 7,000 years old. Its clarity of form, with the freshness of its walls, the crispness of its boundaries, reflects that youth. Geology has not yet had time to soften its edges, fill its basin with sediment, dissect its walls with valleys, bury its structure under subsequent rock. La Garita is nothing like that. La Garita, after 28 million years, is not a visible basin you could stand at the rim of and recognize. The caldera structure, if you were to walk across its floor today, somewhere in the mountains of southwestern Colorado, would reveal itself only in the character of the rock beneath your feet. In the presence of the Fish Canyon Tuff, that distinctive crystal-rich welded ash that, once you know what you are looking at, announces itself through its texture, its composition, the particular way its layers tilt and fracture and expose themselves in the canyon walls and road cuts and stream banks where erosion has cut down to it. But the topography above that rock tells you nothing obvious. The mountains here are just mountains. Old, complex, cut by drainages shaped by 100 subsequent geological events. The caldera is not a hole in the landscape, it is a structure in the rock record, readable only to those who have learned the language of what they are looking at. That is one of the quietly important things about very old geology. The surface ceases to be the record. The surface is just what's left after everything that happened since. The record is in the rock, in the composition and the texture and the structure of the material that accumulated and collapsed and was buried and was then slowly re-exhumed by the same erosion that obscures the form. To understand La Garita, you cannot look at the skyline, you have to look down. And when you look down, what you find, in the exposures that erosion has provided, in the canyon walls and the road cuts and the outcrops where the Fish Canyon Tuff is accessible to study, is the monument. Not a mountain, not a cone or a spire or anything pointing toward the sky. A sheet, a vast, horizontal, buried sheet of welded volcanic rock, hundreds of meters thick in places, extending across thousands of square kilometers of the San Juan region, the frozen record of pyroclastic currents that once moved across a landscape at speeds no living thing would survive. To stand at an exposure of the Fish Canyon Tuff, and there are places in the San Juan Mountains where it does stand exposed, where erosion has stripped away the overlying material and revealed the tuff in cliffs and canyon walls of considerable height, is to stand in front of something that looks, at first glance, like any other rock. Grey, weathered, jointed, fractured by the million freeze-thaw cycles of 28 million winters. But look more closely with the right understanding and the rock begins to tell its story. The crystals are there, the sanidine feldspar in particular, the mineral that gave its name to the Fish Canyon sanidine, the dating standard, visible as pale, slightly glassy laths within the ground mass of the tuff. The welding is there. The rock has a compactness, a density, a fused quality that distinguishes it from the loose tephra that simply falls and accumulates without fusion. In some exposures, the most intensely welded zones show what geologists call eutaxitic texture, the flattened remains of pumice fragments, compressed and fused under their own heat and weight into dark, lens-shaped features within the lighter matrix, like raisins pressed flat in a loaf of bread. Each of those flattened pumice fragments was once a fragment of still hot magmatic foam moving in the pyroclastic current, touching down onto the accumulating sheet and deforming under the weight of everything that came after it, welding into the rock that the current left behind. The thickness of the deposit, in the places where it is best preserved, is striking. Hundreds of meters. Stand at the base of a cliff face of Fish Canyon Tuff and look upward and understand that what you are looking at is the depth of a single eruptive event. The vertical extent of a sheet of fused ash laid down in what geologists believe was a relatively brief episode, measured in days or weeks or perhaps a few months, certainly not in the millions of years over which the magma below had been quietly accumulating its crystals. The speed of the deposition is part of what makes the welding possible. Only if the material arrives hot and thick and fast enough to retain its heat will it fuse. Pyroclastic deposits that cool before they reach sufficient thickness remain loose tephra, the Fish Canyon. Tuff is welded across most of its extent because the currents were so thick and moved so fast and piled up so quickly that the heat had nowhere to go and the particles had no choice but to bond. Thousands of square kilometers, that is the areal extent of the tuff as it is mapped today. And this, remember, is the remnant. 28 million years of erosion have removed material from the edges, dissected the sheet into separate exposures separated by valleys, buried portions under subsequent volcanic and sedimentary deposits, and obscured the original extent in ways that make even the best modern estimates conservative lower bounds. The original sheet was larger. How much larger is a question that depends on how much has been removed, and that is a question geology can approach but cannot fully answer. What we can say is that the tuff exists, mappable and identifiable and measurable, across a region of southwestern Colorado whose scale begins to strain ordinary comparisons. The buried floor of the greatest eruption we know is not dramatic in the way that a summit is dramatic. It does not draw the eye, it does not announce itself. It lies, quiet and ancient and enormous, beneath the mountains, reading itself only to those patient enough to stop and look down at the rock rather than up at the sky. And it is when you begin to appreciate that scale, The thousands of square kilometers, the hundreds of meters of thickness, the 28 million years of patient concealment. That a question that may have been forming quietly in the back of your mind begins to press forward. If the Fish Canyon Tuff is this large, this old, this carefully hidden by time and erosion, how did geologists come to understand it at all? How do you recognize in a range of mountains that has been through tens of millions of years of subsequent geological activity that what you are walking on is the floor of the largest caldera on Earth? The answer to that question is one of the more satisfying chapters in the long story of how human beings have learned to read rock. And it begins not with a dramatic discovery in the field, but with the slow accumulation of mapping, with geologists spending years, decades, cumulatively in the San Juan volcanic field, measuring and describing and collecting, building up a picture of what kinds of rocks were where and in what relationship to each other, and at what structural depths, and with what spatial patterns. The Fish Canyon Tuff, once you are looking for it, is recognizable. Its crystal content is unusual. Its welding is characteristic. Its chemistry is distinctive enough to distinguish it from the other tuffs that the San Juan volcanic field produced during the ignimbrite flare-up. And there were many of those because La Garita, as we will come to understand more fully, was not alone. But recognizing the tuff is different from recognizing the caldera. The caldera requires seeing the pattern of where the tuff is and where it is not, how it thickens toward a central region and thins toward the margins, how the faults that bound the collapse structure align, and what they suggest about the shape and size of the chamber that once lay below. It requires, in short, reading the landscape not as it appears today, but as it was arranged 28 million years ago, stripping away, in the mind, all the subsequent modification and asking what structure best explains the distribution of the rocks you can actually find. This is a kind of detective work that makes few dramatic demands on the body but extraordinary demands on the patience and the geological imagination. It asks you to hold a three-dimensional structure in your mind, rotating it, comparing it against the evidence in front of you, revising your understanding as new outcrops add new constraints, never quite arriving at a final answer because the evidence is always incomplete, but converging, slowly and with considerable effort, on an interpretation that accounts for what can be observed. The result of that long process of mapping and interpretation is our current understanding of La Garita, the 35 by 75 kilometer collapse structure, the original dimensions perhaps reaching toward 100 kilometers before erosion and burial and modification obscured the margins, one of the largest calderas identified anywhere on the continents. And beneath that interpretation, enabling it, supporting it with the kind of numerical precision that makes the story credible and not merely impressive, is something extraordinary that the Fish Canyon Tuff provides, something no other eruptive deposit provides quite as cleanly: the crystals. Those sanidine feldspar crystals that grew slowly in the magma mush before the eruption, that were carried out intact in the pyroclastic currents, that are now visible in every exposure of the Fish Canyon Tuff as pale laths within the welded ground mass. Those crystals are clocks. They contain within their mineral structure the radiogenic isotopes that allow geologists to measure time directly using the decay of radioactive parent atoms into daughter products at rates that physics has established with great precision. The argon-argon method, which uses the decay of potassium-40 into argon-40, is one of the primary tools. The Fish Canyon sanidine, named for the tuff in which it occurs, named in turn for the watercourse in Colorado's Gunnison County, near which the deposit is particularly well exposed, has been measured so many times by so many laboratories using so many different analytical approaches that it has become something unusual in geochronology. It has become a standard, a reference material, a known quantity that laboratories around the world use to calibrate their instruments and verify their methods before they apply those instruments and methods to rocks whose ages are unknown. When a geologist wants to date a volcanic rock from the other side of the world, from a rhyolite flow in New Zealand, or a tuff in Africa, or an ash layer in deep-sea sediment, one of the ways they verify that their measurements are correct is to analyze Fish Canyon sanidine alongside the unknown material using the same instrument and the same analytical conditions, and check that the sanidine gives the expected result. The expected result, established through decades of careful measurement and careful inter-laboratory comparison, clusters around 28 million years. 28.0 to 28.2 million years, depending on the precise decay constants and calibration approaches used. The monster eruption became the master clock. There is something worth sitting with in that. The same event that emptied a magma chamber of 5,000 cubic kilometers of crystal mush that collapsed the ground above into one of the largest calderas on Earth, that buried thousands of square kilometers under a sheet of welded ash hundreds of meters thick. That event also produced, in the crystals it ejected, one of the most useful reference materials in all of geological science. The Fish Canyon sanidine is used today in laboratories on multiple continents to date the ages of volcanic rocks that have nothing else to do with La Garita, that were erupted by entirely different volcanoes in entirely different parts of the world. The precision of the eruption's timing, the clarity of the geochronological signal preserved in those patient, slowly grown crystals, is so high that the eruption serves, in a sense, as a fixed point from which the rest of geological time is measured. The largest eruption we know of is also the yardstick. The wound in the Colorado landscape, buried and obscured and readable only in the rock, is simultaneously one of the pillars on which our understanding of the ages of countless other rocks depends. And UPB zircon dating, which uses the decay of uranium into lead in zircon crystals, also carried out intact by the pyroclastic currents, provides an independent cross-check, placing the tuff at the same position in the radiometric timescale through a completely different decay system, reinforcing the precision and the reliability of the age. 28 million years. 28 million years ago, in the Oligocene epoch, when the climate of the Earth was warmer and the continents were not quite in the positions they occupy today, when the Rockies were younger and the grasses were still spreading across the lowlands, and tens of millions of years before anything recognizable as the human lineage would appear on this planet, the ground shook and the sky went dark, and 5,000 cubic kilometers of rock became pyroclastic currents spreading across a landscape no human eye would ever see. The monument left behind is quiet now. The Fish Canyon. Tuff weathers slowly in the canyon walls of southwestern Colorado. The crystals it contains are removed by researchers and sent to cleanroom laboratories, where they are dissolved and their isotopes counted. The caldera structure sits beneath the mountains, its 35 by 75 kilometer wound still legible in the rock to those patient enough to look for it. And the resurgent dome, that partial healing from below, has itself been subjected to 28 million years of erosion, its form softened and dissected and reduced to a subtle topographic signature that speaks, if you know the language, of pressures that continued long after the main event. This is what deep time does to even the most violent events. It does not erase them entirely. The rock remains, but it quiets them. It spreads them across landscapes so vast and buries them under strata so thick and modifies them through processes so patient that the violence becomes something else, becomes a structure, a pattern, a signal in the isotopes of crystals, a thickness of welded tuff in a canyon wall, a geometry of faults visible only in the data of a geological map. The event that was by any measure the largest volcanic eruption preserved in the geological record of the continents larger than anything human beings have ever witnessed or ever documented or ever will document within the span of recorded history, is present in the landscape of southwestern Colorado today as something you would walk over without knowing. As rock, ordinary, silent, ancient rock that happens if you stop and look carefully and bring with you the patience that geology demands to be telling you everything. And it was not alone. That is the thing that settles over you when you begin to follow the thread beyond La Garita itself, beyond the Fish Canyon Tuff, beyond the single, extraordinary event that has occupied this long night's descent. You pull back from the caldera, from that 35 by 75 kilometer wound in the crust of southwestern Colorado, and you begin to see what surrounds it. And what surrounds it is not ordinary geology. What surrounds it is a landscape that was, for several millions of years, one of the most volcanically violent regions on the surface of the Earth. The ignimbrite flare-up. That is the name geologists give to it, and it is a name that carries more weight than it might first appear to. A flare-up. Not a single event, not a single eruption, not even a single caldera, but a sustained pulse of explosive volcanism that ran from roughly 36 million years ago to approximately 23 million years ago, peaking somewhere around 30 to 28 million years before the present. Which is to say, peaking right at the moment La Garita was building toward its culminating discharge. The Fish Canyon Tuff was the loudest note in a very long, very violent composition. Think of what that means. The flare-up lasted at its broadest something in the range of 13 million years. 13 million years is a span of time so large it nearly loses meaning. It is longer than the entire duration of the Pleistocene epoch, the Ice Ages, the rise and extinction of dozens of mammal lineages, the entire history of our genus from the first rough-napped stone tools to the present moment. All of that fits inside a fraction of the flare-up's duration, and across that span, across that immense corridor of geological time, the southern Rocky Mountain region produced eruption after eruption after eruption of a scale that has no parallel in anything a human being has ever seen. The San Juan volcanic field alone, that broad expanse of volcanic terrain in southwestern Colorado where La Garita sits, hosts at least 15 to 20 identified calderas. 15 to 20 of them, collapsed, emptied, foundered structures, each one a record of a magma chamber that grew large enough and pressurized enough to discharge catastrophically and then cave in on itself, leaving the same kind of wound that La Garita left on varying scales scattered across the landscape. Some of them are smaller than La Garita, some of them are respectably large in their own right. Taken together, they represent a density of supervolcanic activity that is extraordinary even by the generous standards of geological history. If you had stood in what is now southwestern Colorado at the peak of the flare-up, and if you had survived, which is a condition so hypothetical as to be almost meaningless, because surviving in that landscape during that interval would have required circumstances that biology does not generally provide. You would not have seen what you see today. You would not have seen the relatively quiet, eroded, beautiful mountains of the San Juan Range, those peaks softened by tens of millions of years of ice and wind and water. You would have seen something closer to a planetary surface in the process of remaking itself. Flat sheets of welded tuff stretching to every horizon, broken by the sunken depressions of caldera after caldera, the air above them thick with the suspended debris of events that had occurred years or decades or centuries before and had not yet settled from the stratosphere. The Rockies in that interval were not the Rockies. They were a supervolcanic field of a kind the modern world simply does not have. And at the center of all of it, or very close to the center, at the peak of it, La Garita discharged 5,000 cubic kilometers of material and left the largest collapsed structure in the record, the loudest voice in the chorus, the one that all the others were, in a sense, building toward and building away from. The climactic event of a multi-million-year pulse of violence that had been gathering itself through slow, crustal processes, through the patient manufacture of silicic magma in chambers deep in the crust, through the repeated emptying and refilling and repressurizing of those chambers over geological timescales. The flare-up itself had a cause, of course. Nothing in geology happens without a cause, without a chain of processes running back through earlier events, earlier configurations of the Earth, earlier states of the slow machinery that moves plates and melts rock and raises mountains and lowers them again. The driver of the ignimbrite flare-up was something happening far beneath the western edge of the North American continent, in the dark and immense zone where one tectonic plate was sliding beneath another. The Farallon Plate. It is gone now, or almost gone. It has been consumed, subducted, swallowed by the deeper mantle over the course of millions of years of ongoing tectonics, and what remains of it survives as scattered fragments bearing names like the Juan de Fuca Plate and the Cocos Plate, recognizable to geologists as the last remnants of something once much larger. But in the Oligocene, in the time of the ignimbrite flare-up, the Farallon Plate was still a substantial presence, still sliding eastward and downward beneath the western margin of North America, still feeding the deep geological machinery of the continent's interior. And the geometry of how it slid matters enormously. The Farallon Plate had been, for a long period before the flare-up, subducting at a relatively shallow angle, diving not steeply into the mantle, but at a low, flat trajectory that carried it far inland beneath the continent before it began to sink more deeply. This shallow subduction had its own effects on the geology of Western North America, effects that geologists have spent considerable effort trying to understand and reconstruct. But then, around the time of the flare-up, something changed. The angle of the subducting slab began to steepen. The Farallon Plate began to roll back, to sink at a more acute angle, to retreat from beneath the continental interior. Slab rollback. That is the process. And what slab rollback does when a subducting plate changes its angle and retreats is open a window. Not a literal window, but a geological one. When the slab steepens and pulls back from beneath a region of continent, the hot, relatively buoyant rock of the underlying mantle, the asthenosphere, that layer of partially molten rock beneath the rigid plates, rushes in to fill the space. Hot mantle wells up from below, and hot mantle rising beneath continental crust is something very specific and very consequential to that crust. It melts it, partially unevenly along zones of lower melting point and higher heat, but it melts it. It generates magma, and in the thick, silica-rich crust of the continental interior, the magma generated tends to be silicic, rich in silica, high in viscosity, capable of holding dissolved gas under enormous pressure and releasing it with catastrophic violence when that pressure is finally relieved. This is the engine, the Farallon Plate rolling back, the asthenosphere rising to fill the space, the heat transferring into the base of the continental crust, the crust melting and generating chamber after chamber of silicic magma, those chambers growing and pressurizing and eventually discharging in the sequence of eruptions that constitutes the flare-up. The ignimbrite flare-up was, in the deepest sense, the surface expression of a continent-scale change in the plumbing of the Earth. The eruptions were symptoms. The disease, if one wishes to use that language, although the Earth does not get sick, only configured differently, was the reorganization of a subducting plate across a span of millions of years and thousands of kilometers. La Garita was the loudest symptom, the 5,000 cubic kilometers, the 35 by 75 kilometer wound. The Fish Canyon Tuff, spread across thousands of square kilometers, fused by its own heat into stone. All of it traceable in the end to a change in the angle of a plate that has since largely vanished into the mantle, consumed by the very process that created the conditions for the largest eruption we have managed to find in the geological record of the continents. There is something quietly astonishing in that chain of causation. The largest volcanic eruption preserved in the rock record was not caused by a dramatic geological anomaly, not by some unique and freakish convergence of impossible conditions. It was caused by ordinary plate tectonics, by the ordinary, ongoing, patient movement of the planet's rigid outer shell over the softer rock beneath it, by a change in angle, by the rise of hot mantle into a vacated space, by melting and accumulation and pressure and release. The same processes that build ordinary volcanoes, the same fundamental machinery, run at a larger scale over a longer time with a larger volume of crust available to be melted and mobilized in a region where the conditions happen to align just so. Extraordinary in its outcome, ordinary in its mechanism. That perhaps is one of the more unsettling things about it. And then there is the question of how we know all of this, how geologists working in the modern world looking at rock that is 28 million years old have managed to reconstruct not just the existence and the scale of the Fish Canyon Tuff, but its precise age, its mineralogy, its eruptive mechanism, the geometry of the collapsed structure that produced it, the tectonic context that built the magma chamber that fed it. This reconstruction is the work of many researchers across many decades, using techniques that range from the physical mapping of exposures in the field to the analysis of isotopes in individual mineral grains extracted from the tuff and measured in clean room laboratories. The dating of the Fish Canyon Tuff is one of those stories that has a quiet elegance to it. The tuff contains crystals of a mineral called sanidine, a form of feldspar chemically related to some of the most common minerals in the Earth's crust, found in many volcanic rocks but particularly abundant and well-formed in the Fish Canyon Tuff. When the magma cooled and the crystals formed, they trapped within their lattice structures a specific ratio of chemical elements, including potassium, which over time decays into argon at a known and measurable rate. This is the basis of argon-argon dating, the RR method. By measuring the ratio of different argon isotopes in a crystal, geologists can calculate how long it has been since that crystal formed, since the clock was reset by the heat of crystallization. The technique is exquisitely precise, capable of resolving ages to within tens of thousands of years on material hundreds of millions of years old, and the Fish Canyon sanidine has been dated in this way so thoroughly by so many different laboratories, using so many different sample preparations and analytical approaches, that the result, at approximately 28.0 to 28.2 million years before the present, is among the most precisely and reliably known ages in the entire geological record. But the story does not stop there, because the Fish Canyon sanidine has become something more than simply a well-dated sample. It has become the standard by which other samples are dated. When a geochronologist wants to measure the age of an unknown volcanic deposit using the RR method, one of the things they need is a reference material of known age, a standard against which they can calibrate their measurements, account for the behavior of their instruments, and convert the raw numbers that their mass spectrometers produce into actual dates. The Fish Canyon sanidine is one of the most widely used standards in the world for precisely this purpose. Laboratories on multiple continents routinely irradiate samples of Fish Canyon sanidine alongside unknown samples, measure both, and use the known age of the sanidine to calibrate the ages they derive for the unknowns. Which means that the Fish Canyon Tuff, the deposit left by what may be the largest volcanic eruption preserved in the geological record of the continents, is not merely a monument to its own violence. It is the master clock. It is the reference point. When geologists date a volcanic deposit in Japan, or a lava flow in Ethiopia, or a tuff bed in New Zealand, they may be anchoring those dates, ultimately, to crystals that formed in the magma chamber beneath the Garita Caldera 28 million years ago. The monster became the measure. The largest eruption we know of is also, in a quiet and practical and entirely unintentional way, the yardstick by which we measure everything else. That is a strange and beautiful thing, not in any mystical sense. There is no intention in it, no design, only the contingency of chemistry and physics and the particular abundance and quality of the sanidine crystals that the Fish Canyon magma happened to produce, but strange and beautiful nonetheless. The Earth's most violent preserved act of geological discharge became, because of the minerals it crystallized and the precision with which those minerals can be analyzed, the instrument by which we navigate deep time. And deep time in the end is what has made La Garita nearly invisible. This is the last piece of the paradox the title set before you at the beginning of this long night. Not just why there is no mountain, that question was answered in the mechanism, in the caldera collapse, in the horizontal welded sheet instead of the vertical cone. But why is it that the largest eruption in the geological record of the continents sits in a landscape that most people drive through without noticing? Why does it take a geological map and a trained eye to recognize what happened there? 28 million years. That is the answer. And it is an answer that requires some sitting with, because 28 million years is not a number that the human mind is equipped to feel, only to think about. We understand 100 years because grandparents and grandchildren bracket it. We can stretch toward 10,000 years because it encompasses the entire span of recorded human civilization, everything from the first cities of Mesopotamia to the present. 100,000 years is harder but not impossible. It reaches back past the beginning of behaviorally modern Homo sapiens into the deep prehistory of our species. But 28 million years is somewhere else entirely. It is a span in which entire mountain ranges have risen and eroded and risen again, a span in which continents have shifted their positions by hundreds of kilometers, a span that encompasses the entire evolution of the order of primates from which all monkeys, apes, and human beings descended. At 28 million years ago, there were no grasslands. The great open savannas that would eventually allow our ancestors to walk upright and throw spears and develop the anatomical and cognitive architecture that eventually produced a species capable of caring about the age of volcanic deposits. Those savannas did not yet exist. The world was warmer and wetter and covered by different vegetation in different configurations than anything we see today. The ancestors of what would become horses were small, multi-toed browsers in forest undergrowth. The ancestors of what would become elephants were in different places than elephants are now, in different configurations of the Earth's land masses. Whatever was happening biologically in the living world of 28 million years ago has no direct continuity with the world we inhabit except through the long chain of descent that connects everything living to everything that came before it. And in that world, on a continent that looked different from the one that exists now, in a region of what would eventually become southwestern Colorado, the Earth opened in a way it has not opened since. 5,000 cubic kilometers. The ground shook with a violence that has no comparison in any instrumental record ever made. The sky above what is now the San Juan Mountains would have been, for some period whose duration remains uncertain, days, weeks, perhaps longer, unrecognizable as sky. A column of material rising to heights that no material has risen to in any eruption any human being has ever witnessed. Pyroclastic density currents spreading outward across the landscape at speeds that would have made them indistinguishable to any hypothetical observer close enough to see them, from the landscape itself simply becoming something else, becoming a moving, incandescent, lethal mass that swallowed terrain and deposited rock and kept moving. And then it stopped. The chamber emptied, the pressure dropped, the ground fell inward and downward, and the caldera formed, that vast depression, 35 by 75 kilometers across, settling into the silence that follows the end of the world's loudest event. And the world continued. The heat dissipated, the debris settled and compacted and fused and became stone. The sky cleared over timescales that are long by human standards and brief by geological ones. And the long process of modification began. The erosion, the burial, the resurgence from below, the further eruptions nearby, the continued action of weather and water and ice over millions of years. No VI-8 eruption has occurred within recorded human history. Not one. The category exists, VI-8, more than 1,000 cubic kilometers of material discharged in a single eruptive event. But no human being, in all the tens of thousands of years of human history for which we have any record, has witnessed one. The largest eruption in recorded history is Tambora, in 1815 on the island of Sumbawa in what is now Indonesia, which produced something on the order of 100 to 150 cubic kilometers of total material. And Tambora was catastrophic. Tambora killed tens of thousands of people directly, and the aerosols it injected into the stratosphere disrupted global climate sufficiently that 1816 became known as the year without a summer, with crop failures across the northern hemisphere and the attendant misery and starvation that agricultural failure produces. Tambora, at VEI-7, was the largest eruption any living person had ever heard of, and it was devastating. La Garita was 50 Tamboras, and no human being has ever seen anything like it. The most recent events in the VEI-8 category that we have been able to identify are considerably more recent than La Garita, but still far beyond the reach of recorded human history. The Orowanui eruption, which produced the Taupo volcanic center in what is now New Zealand, occurred approximately 25,500 years ago, 25,500 years. That is deep in the Upper Paleolithic, in the middle of the last glacial maximum, when ice sheets covered substantial portions of the northern hemisphere, and human beings in New Zealand, had there been any, which there were not, as humans would not reach New Zealand until roughly 700 years ago, would have experienced something that no modern person and no recorded human has ever experienced. The Orowanui eruption discharged roughly 1,100 cubic kilometers of material. It was a VI-8 event, just barely over the threshold, and it happened at a time when our species existed, but when everything we conventionally call civilization was still tens of thousands of years in the future. And before that, the Toba eruption in what is now Sumatra in Indonesia, approximately 74,000 years ago. Toba is in a different class even within the VEI-8 category. It discharged somewhere around 2,700 cubic kilometers of material, making it far larger than Orowanui, and the geological evidence of its ashfall has been found across South Asia, in ice cores, in marine sediments, across enormous distances that speak to the scale of the atmospheric loading it produced, 74,000 years ago. At that point, anatomically modern Homo sapiens existed as a species. We had evolved, we were present on Earth. But we were a relatively small and scattered population, and the question of how severely the Toba eruption may have affected human populations is one that researchers continue to explore. But none of these events, not Orowanui, not Toba, not any other VEI-8 in the record, occurred within the span of what we call history. History, in the broad sense, encompasses perhaps 10 or 12,000 years of agricultural civilization, of writing, of cities and trade, and the accumulation of human knowledge in durable form. In all of that span, the Earth has not produced a VI8, not once. The planet has been, from the perspective of the super-eruption category, remarkably quiet during the entire interval in which human beings have been literate, agricultural, and capable of recording what they witnessed. This is, depending on how you hold it, either comforting or sobering, and perhaps it is both simultaneously. Comforting because it means that the kind of event this night has been about, 5,000 cubic kilometers, a caldera the size of a small metropolitan area, a welded sheet hundreds of meters thick across thousands of square kilometers, is not something that lurks just around the temporal corner of human experience. The most recent VEI8 was 25,000 years ago. The one before it was 74,000 years ago. La Garita, which dwarfs them both, was 28 million years ago. These events are real, they are documented in the rock, they are part of the Earth's history, but they are ancient events, finished events, events that the planet has long since absorbed and quieted and covered with the ordinary processes of erosion and deposition and gradual modification. The wound is healed, not completely. The caldera still exists, the rock still records it. The isotopes in the Fish Canyon sanidine still carry the chemical signature of what happened there. But the violence is finished. The pressure that built over millions of years and discharged in a single catastrophic event dissipated 28 million years ago, and the slow work of geological time has been converting that violent release into landscape ever since. The tuff is stone. The caldera is topography. The resurgent dome is a subtle rise in the landscape that most people would not recognize as the signature of anything unusual. The Farallon plate that drove the whole sequence has largely disappeared into the mantle. The ignimbrite flare-up has ended. The San Juan volcanic field is quiet. There is something in that quietness worth sitting with as this night comes to its end. We live in a world shaped by forces of almost incomprehensible scale and violence. Plate tectonics, volcanism, erosion, the slow grinding of geological time across all the structures the Earth builds and rebuilds and dismantles. The landscape under our feet is a record of events far larger than anything in human experience, written in a language, mineralogy, stratigraphy, geochronology, that takes years to learn to read. La Garita is one chapter in that record, an extraordinary chapter, perhaps the most voluminous single chapter in the record of continental explosive volcanism, but a chapter in a longer book, part of a sequence, embedded in processes that began before it and continued after it, and are still, in their modified and quieter current forms, ongoing. The Fish Canyon. Tuff lies in the canyon walls of southwestern Colorado. Researchers take small samples from it and dissolve them and count isotopes, and derive, from those counts, dates that anchor the entire Oligocene timescale and serve as calibration points for geochronology on the other side of the world. The caldera geometry is mapped from the distribution of deposits and the pattern of faults and the slight topographic expressions that survived 28 million years of erosion. The crystal mush that produced it, that thick 45% crystal slurry that somehow discharged 5,000 cubic kilometers, is studied in thin sections under polarized light in university laboratories, its mineral compositions and textures analyzed for what they reveal about the conditions in the magma chamber before the eruption, the temperature and pressure and volatile content that eventually made the discharge inevitable. And the mountains of the San Juan range stand in the sun and the wind and the snow, their summits and ridgelines and valley walls all composed in part of the evidence of what happened there. Not as a monument to violence. The violence was not intended to leave a monument. It was a geological process, as indifferent to meaning as all geological processes are, simply the release of pressure that had accumulated beyond the point of containment. But the record is there. Hundreds of meters of welded tuff in the walls of canyons, the subtle bowl of the caldera in the broader topography, the crystals of Fish Canyon sanidine in clean room laboratories, their argon isotopes still speaking millions of years later of the moment they formed in a magma chamber that no longer exists beneath a caldera that has been eroded almost beyond recognition. The biggest eruption in Earth's history left no mountain. It left a wound, and the wound filled with rock, and the rock became the landscape, and the landscape became the quiet mountains of southwestern Colorado, and the quiet mountains of southwestern Colorado are, if you know how to read them, still saying exactly what happened. Everything. Every cubic kilometre of the 5,000. Every degree of temperature in the pyroclastic currents. Every year of the 28 million that have passed since the ground fell and the magma chamber breathed its last. The Earth is not in the habit of forgetting. It simply encodes its memories in a language that requires patience to learn and great age to accumulate and the long, slow, methodical tools of science to read. And when you do learn to read it, even a little, the world becomes a different place. The canyon wall becomes a library. The crystal in the rock becomes a clock. The broad sunken plain in the mountains of Colorado becomes the record of the loudest thing that ever happened on this continent within the reach of geology's instruments. And the loudest thing, it turns out, went down and outward, not up. Left a floor, not a summit. Made its monument horizontal in the welded stone of the Fish Canyon Tuff, spread across the landscape in the patient silence of deep time. Not a mountain to look up at, a foundation to stand on without knowing, as you walk through those mountains on a quiet afternoon, that you are standing on the aftermath of the largest eruption we have ever found. That is worth knowing, even lying here in the dark at the end of a long night's descent into the deep past of the Earth, perhaps especially then. If you have come this far and found something in it, if the slow accumulation of these ancient facts has been company of some kind on the way towards sleep, and if you feel moved to say where in the world you are listening from tonight, I would genuinely like to know. The comments are there, and I do read them. There is something particular about the geography of these nights. The idea that someone in New Zealand and someone in Scotland and someone in Colorado, perhaps near the San Juan Mountains, perhaps not far from the Fish Canyon Tuff itself, might all be falling asleep to the same long story about the same buried rock. I find that worth knowing. There are more stories here of the same slow and careful kind. The Earth has a great many ancient things to say, and this channel moves through them at its own unhurried pace, the way geology itself moves. Not quickly, never quickly, but with the kind of persistence that turns even the largest events into landscape. You have done enough for one night. The questions the title asked have been answered as fully as the record allows. The mountain is gone because it collapsed. The eruption is invisible because 28 million years of deep time have converted it from violence into stone. The stone is read by instruments and patients, and the accumulated knowledge of researchers who have spent careers in canyon walls with sample bags and notebooks and mass spectrometers. And the stone, in the form of the Fish Canyon sanidine, now calibrates the clocks that date the rest of the planet. Let all of that settle. Let the weight of 28 million years be something that moves through you rather than something you need to hold. The forces that shape that landscape finished their most violent work long before anything human existed to witness or to worry about it. The caldera is quiet. The tuff is stone. The San Juan Mountains stand in their eroded, patient, ancient beauty. and the wind moves through them tonight exactly as it moved through them last night, and will move through them long after any night we might be present for. Put down whatever remains of the day. The canyon walls of Colorado are not going anywhere. The Fish Canyon Sanodyne has been counting time for 28 million years and will continue without any help from us. Good night. Sleep well. Tie off here at the Wisdom Docks. The tide will wait till morning.